Welcome back. In this video we are going to talk about something called strong and weak acids. We are also going to talk about something called strong and weak bases. So if you remember from the previous video, our definition of an acid is it's a material that's capable of donating H+. Turns out that some acids, there are many different kinds of acid molecules, some acids are good at donating H+, and if you're good at donating H+, we call you a strong acid. And I'll talk about what it means to be good in a little while. Other acids are not so good at donating H+. They'll do it, but they're not very good at it. And if you have this kind of acid, it's called a weak acid. Usually the ability to donate H+ is measured by the ability that the acid has to donate H+ to water. So water is kind of our reference when we compare acids to each other. How good is your acid at donating an H+ to water? Is it really good? Well, then it's a strong acid. If it's not so good, it's a weak acid. So here is an example of a strong acid. I mentioned this in a previous video, but this is called nitric acid over here. And this is the H+ that's going to get donated, and we are trying to donate it to water. If you look over on the right side, when the HNO3 or when the nitric acid donates its H+ to water, it turns into NO3 with a negative charge, and it turns one of the water molecules into H3O+, which if you remember is called a hydronium ion. And there is a mathematical way of describing and figuring out whether an acid is strong or weak, and we will get to that in a video later on. But here there's a big tip-off in this reaction, and the tip-off is that this is a one-way arrow. If you have a one-way arrow, that is chemistry shorthand for telling you, look, this reaction is only going to go from left to right, or almost exclusively from left to right, which means that this acid here is really good at donating its H+ to water. Because if it wasn't so good, then you would have a two-way arrow, because stuff on the left side could turn into the stuff on the right, but there's also a pretty good chance that the stuff on the right side could turn into stuff on the left. But since this is a one-way arrow, it's basically telling you that almost all of the time, the stuff on the left side will be converted into the stuff on the right, which means strong acid. This is a different acid. In the second reaction, it looks almost the same. The top acid is HNO3, the bottom acid is HNO2. This is called nitrous acid, in case you care. And we are looking at its ability to donate its H+ to water. You can see that when it does donate the H+ to water, it turns into NO2 with a negative charge, and it turns one of the water molecules into H3O+, in a very similar way as to what happened in the reaction above. But if you look at the way that this equation is written, there's a two-way arrow. What that means, again, stuff on the left can be converted into the stuff on the right, but some of the stuff on the right can also be converted into the stuff on the left. And because of this two-way arrow, that's a big tip-off that nitrous acid, this stuff over here, is a weak acid. So that is probably the simplest way if you have that equation, if you have those types of equations shown to you, you can tell whether something is a strong or a weak acid. There's a more mathematical way of describing or figuring out whether an acid is strong or weak, and it turns out that it's related to the equilibrium constant, which is why we talked about the equilibrium constant before we talked about this stuff. There are also different kinds of bases, and we can put them into categories based on whether they are strong or weak as well. So if you remember, this is our definition of what a base is. It's a material that's capable of accepting H+, or a material that's capable of making OH- when you mix it with water. Some bases are good at accepting H+ or making OH-, and if you're really good at that, we call you a strong base. Other bases are not so good. They will do it, but they won't do it very well. We'll call those weak bases. And again, usually bases are measured as to whether they're strong or weak based on their ability to accept H+ from a water molecule. Or it should also say, or the ability to make OH- when it's mixed with water. So if you're good at accepting H+ or you're good at making OH-, we're going to call you a strong base. If you're not so good at accepting H+ or not so good at making OH-, we're going to call you a weak base. So here is an example of a strong base, and you're going to see the big tip-off again. This is called sodium hydroxide. There's the OH- that's going to get released when you mix it with water. And if you look, there's a one-way arrow. And that is saying this stuff over here on the left is almost exclusively going to be turned into the stuff on the right, and the reaction probably isn't going to go backwards very much. So NaOH, or sodium hydroxide, is a strong base. This is another reaction that I showed you in the previous video. This stuff is called ammonia, and if you mix it with water, every once in a while one of the water molecules can donate an H+ to the ammonia, and it turns the ammonia into this thing over here, also ends up making H+. But if you look at the way the equation is written, there's a two-way arrow, which is a tip-off that the reaction can go in both directions, left to right as well as right to left, which means ammonia is a weak base. And what you'll see is there is also a mathematical way of figuring out whether a base is strong or weak, and we're going to talk about that in, I think, the next video, maybe the next video. Here you can do this particular exercise. You can pause the video and think about this. A couple of things. Identify the acids and bases on the left side of the equation, so just the left side. And second question, is this a strong or is there a strong or a weak acid on the left side of the equation? So if you pause the video, you can think about that. If you unpause the video, well, there's a two-way arrow here. So whatever it is, it's going to be weak. Second thing is, which one is the acid in this case? Well, it could be the water, because water can sometimes act like an acid, or it could be this stuff over here. What you have to do to figure out who's an acid and who is a base is you have to count the hydrogens. How many hydrogens are here with that molecule? There are 2. And on the other side of the arrow, how many hydrogens does it have? Well, it has 1. So what that means is, whatever this stuff is, it must have donated an H+, because it started with 2 and it ended up with 1. So this thing is an H+ donor, which means it has to be an acid. And obviously, if this is an acid, this must be a base, but let's just sort of think through this just to make sure. The water starts with how many hydrogens? Well, it starts with 2. Ends up with how many hydrogens? Ends up with 3. So if this started with 2 hydrogens, ended up with 3, this must have accepted an H+, which means this must be the base. So this is the acid on the left, this is the base on the left, and that's how we figure it out. And this particular acid is a weak acid. There is a term that I want you to know, because it's going to come up when we talk about the mathematical definition or the mathematical way of figuring out whether acids and bases are strong or weak. The term is conjugates. Here is the reaction. Remember, this is called nitrous acid, and we said this is this is the acid over here. In this case, the water is acting like a base because it's going to receive the H+ from this stuff over here. But if you look at this reaction, this is an acid. It starts with 1 H, ends up with 0 H's. But if the reaction runs in reverse, this stuff over here acts like a base, because if you run the reaction backwards, this starts with no hydrogens and it ends up with 1 hydrogen. So this must accept when the reaction runs backwards. So we say that this stuff is a base. The term conjugate comes up here. This is an acid, and on the other side, this is called its conjugate base. Conjugate in this case means it's married to or it's tied to this other thing on the other side. So if I said, hey, what's the conjugate of nitrous acid? You would look at this equation and say, oh, that's the stuff over here, NO2 with a -1 charge. Same thing, same word gets used with bases as well. In this particular reaction, the water is acting like a base because it starts with 2 H's, ends up with 3. This is the base on the left side. This is its conjugate. In this case, it's going to be acid on the right side, because if you run the reaction in reverse, this is the thing that can do the donating if the reaction runs backwards. So acid turns into its conjugate base, base turns into its conjugate acid. And you can use the same terms when the situation is reversed. Down here, this is a base. This is called ammonia again. This is going to pick up an H+ from the water. So the water is going to give an H+ to the ammonia. So if the water is giving the H+, this is the acid. But the acid will turn into conjugate base on the other side. And this base will turn into conjugate acid on the other side. So this is the base. This is its conjugate acid, this is the acid, this is its conjugate base, and that's what I want you to know about the term conjugates. That term is going to show up in subsequent videos, so you should know it. So this is the last slide for this video. You can look at this reaction and pause the video and identify the acids and bases and their conjugates. So if you unpause the video, this must be the acid in this case because it starts with two H's, ends up with 1. So this must be its conjugate base over there. And if this is the acid, the water in this case must be the base because it's going to accept an H plus from this acid over here and it's going to turn into H3O plus. So this is the base and this must be its conjugate acid on the right side. And if you run the reaction in reverse, the H3O plus can donate an H plus back to this thing. So this is acting like an acid and that's acting like a base. Okay, so we are done with definitions of acids and bases. We are also done with conjugate acids and bases. We're done with weak and strong acids as well as weak and strong bases. In the next video, we are going to do more math. And that's the end of this video. See you in the next one.
Yeah, it's pretty clear. I ain't no size dude, but I can shake it like I'm supposed to do. 'Cause I got that boom boom that all the boys are chasing, all the right junk in all the right places. I see those